Alright guys, so I thought I'd do something a little different, and that's going to be projecting my screen and showing you the work below. I wanted to give you a few more examples on similar type problems to the one in the first video. So what I'm going to do is I have this section from the book scanned into my computer, and we're going to do a couple of problems. So let's do the first one. It says each side of a cardboard square is 12 inches. So I have a square that's 12 by 12. Bring that in a little closer. What is the maximum volume? So what am I looking for? Maximum volume of a box that can be made from the square by cutting congruent squares from the corners and turning up the four sides. So, you know, this is very similar to the last problem, except instead of a rectangular piece of cardboard, we have a square one. Well, that's nice because if we cut out these little squares here, this side becomes 12 minus 2x, and so does this side, right? So volume, that's what we're looking for, is length times width times height. So the volume formula is going to be 12 minus 2x quantity squared times the height. Got a formula. And I'm going to go ahead and simplify that. So let's FOIL this out. We're going to have 144 minus 48x plus 4x squared times x, and now I'll distribute this x back in. So we're going to have 4x cubed minus 48x squared plus 144x. So that's my v of x. I'm good. I've got a formula, a function in one variable. Now I have to find my domain. Well, again, I could cut 0 squares out, so I'm not going to have any box. So I'm going to start with 0. And the nice thing about a square base is that since each side is 12, well, if I cut a 6 by 6 square out, I'm cutting all the paper, right? I'm not going to have any paper left or cardboard left to make a box. So 6 is going to be the end point of that interval. So that's my domain. So let's take a derivative. I'm going to have 12x squared minus 96x plus 144. I want to set that equal to 0. So I'm going to factor out a 12. We're left with x squared minus 8x plus 12 equals 0. Again, if I multiply through by the 12, it goes away. So I can factor this trinomial to x minus 6 times x minus 2. So we get x is equal to 2 and 6. Well, 6 is already an endpoint of my domain, so it's there. 2 is the only critical number in between those 2 points. So what I have to evaluate is v of 0, v of 2, and v of 6. Well, here's v. If I plug a 0 in, it's clear that it becomes a 0. And likewise, if I plug the 6 in, I'm going to get a 0. Why? Because we took the derivative, set it equal to 0 and solve, and 6 was a 0 of the derivative. So it's going to be 0 as well. So really the only one that I'm curious about now is this 2. If I plug the 2 in, I'm going to have 2 cubed is 8 times 4 is 32, minus 48 times 4, plus 144 times 2 is 288. And if I compute that up, I get 128. So what I know is that I would have a maximum volume of 128 cubic inches when squares are cut out of all 4 corners that have size or side length of 2 inches. I hope that's okay. The next one that I liked was number 7 here. So again, this is from your best book and it's page 281. Number 7, we want to build a cardboard box with no top, with a square base that holds 108 cubic inches of something. Okay, so the volume is 108 cubic inches. They want you to find the minimum area of the cardboard needed. So that means we need the surface area in this box. So I know my base has to be square. So, I'm going to have this little, I can't draw, right? So, I don't know. There's a box with an open top. And since I don't know what the base is, my square base, I don't know the dimensions, I'm going to say it's x by x. So the area of this base is x squared. And I know the formula for the surface area, but I may forget that if I'm a kid, right? I know it, so in this case it would be length times width of the base, right? Plus 2 times width times height, plus 2 times length times height, right? For the front, the back, and the 2 sides. But you don't have to remember that. Right here you have the area of the base, which is x squared, and you have to figure out, what is the height of this thing. So we know that volume is length times width times height. So in this case, volume is x squared times height. Volume was given to be 108, so the height is equal to 108 over x squared. So the height of this box, this height, is going to be 108 over x squared. Well, guess what? I have 4 sides of the box. This length here is x, this is 108x squared. And the height's going to be the same all the way around, and since it's a square base, so is the length of the side of the base. So my area formula is going to be the area of the base plus 4 times 108 over x squared times x, right? So in other words, if I did the front here, the area would be x times 108 over x squared. So there's an x in there. It's hard to see. And this x is nicely going to cancel with one of those x's. And 4 times 108 is 432. So a of x is equal to x squared plus 432 over x. Now, the domain. Again, I could have a piece of cardboard size 0, and by the way, I can't include 0 because if x is 0, then I have 0 in the denominator. But I can start at any little point right after 0. So 0 not inclusive, and technically speaking, a piece of cardboard could be 20 acres big if I wanted it to be. So it's going to go to infinity, because technically speaking, I can buy a piece of cardboard as big as I want. Okay, so this is interesting because if I take the derivative of this, I'm just going to write the area formula like this. So that way when we take the derivative, it's easier. We're going to have 2x minus 432x to the minus 2, or 2x minus 432 over x squared. And I can't test my 2 endpoints, but let's set this thing equal to 0 and see what happens. I'm going to multiply through by x squared. So I'm going to have 2x cubed minus 432 is 0. And so that means 2x cubed is 432. So x cubed is 216. So x is equal to 6. So I have this critical number in between 0, which I cannot include, and infinity, which I cannot include, and now I have to find out, is this a minimum? How am I going to do that? Well, if I don't have a calculator, I'm going to use the second derivative test. Second derivative test says if you have the derivative of a function at some point equals 0 and the second derivative at that point is positive, then your graph's going to be concave up, so you're going to have a relative minimum. And if the derivative at that point equals 0 and the second derivative at that point is negative, well, then you're going to have concave down or maximum. So this is the thing I want, and I want to see if it's true. So what I know is f prime of 6 equals 0. I want to see what happens with the second derivative. So let's see, a prime of x was 2x minus 432x to the minus 2. So let's find a second derivative. That's going to be 2 plus 864x to the minus 3. And that's 2 plus 864 over x cubed. So if I evaluate that second derivative at 6, I'm going to have 2 plus 864 over 216. Well, that's a positive plus a positive, gives me a positive. So my second derivative is positive, and that means that I'm going to have, my function is going to be concave up, and I'm going to have a relative minimum at x equals to 6. So all I have to do now is plug that 6 into the original area function to see how big my cardboard has to be. And the original function again was x squared plus 432 over x. So if I evaluate that at 6, it's going to be 36 plus 432 over 6. And I'm going to use my calculator. Is 108. And so I would need a piece of cardboard, 108 square inches, excuse me, in order to construct a box that has a volume of 108 cubic inches. I hope that makes sense. Mull that over, and there'll be some more to come.